Hi everyone, in this video we are going to be talking about tree thinking. And what I mean by that is a way for us to think about how species are related to one another and how recently they diverged from each other. So drawing a phylogenetic tree, or we're also going to use the word cladogram, is a nice way to show how all organisms are related to one another, and that either more recently or farther back, there's a point of shared common ancestry between any living thing and any other living thing. And sometimes for two organisms, like for humans and bacteria, you would have to go really, really, really far back to find that point of common ancestry. Whereas if you're looking at us and a chimpanzee, maybe, the point of common ancestry would be a lot more recent. But drawing these evolutionary relationships in a tree form really shows that there's sort of a shared path that a lot of organisms had with other organisms, at least for a certain amount of time. And this is showing an artistic rendition of a phylogenetic tree. And we're going to be using the word cladogram for the rest of our unit. And I just want to point out the difference really quickly because you'll see both if you do any research online. A phylogenetic tree has the length of the branches on the tree represent time, evolutionarily speaking. And the distance between the branches represents sort of the distance between two species, whereas a cladogram is a lot more of a simple diagram, and only the connections between the branches are the only things that matter. So phylogenetic trees are just a more accurately scaled sort of diagram, and the other option is a cladogram, where we have the relationships between species are represented in a certain way, but the length of the branches doesn't really mean anything, and it's not to scale. You can think of it that way. So when you look at a cladogram like this, what we can see is that all of these organisms, and we can think of them as being species, we can think of them as being families, you can put different types of groups or taxa on the tips of the branches, but the point is that they're all related to one another. So swordfish, frogs, alligators, and T-Rex are all related. And we can see that at a certain point, either more recently or further back, they had common ancestors that they shared. And the way to find a common ancestor is by looking at a node that connects two of the branches. And so, for example, in this diagram, we can see that alligator and T-Rex, their branches converge at this node labeled C. And so we would say C was the common ancestor that gave rise to both alligators and T-Rex. And then if you go further back, this point labeled B is the node where we had a common ancestor that gave rise to frogs and gave rise to the common ancestor of alligators and T-Rex. And then even further back, A is the common ancestor of swordfish and the common ancestor of frogs and species C, which then gave rise to alligator and T-Rex. So two organisms, if you're looking at a cladogram like this, are going to be more closely related if they shared a common ancestor more recently. So let's compare an alligator and a T-Rex. We can see that they shared a common ancestor at C, but if we wanted to find the common ancestor of alligator and a swordfish, we have to trace the line back all the way back to A. And at point A, then we can draw a line to swordfish and we can draw a line to alligator. So alligator and T-Rex are more closely related because they shared a more recent common ancestor at C, and alligators and swordfish are more distantly related because they don't share a common ancestor until back at point A. So we can use cladograms to figure out how closely related different organisms are. And this is one way to draw a cladogram with sort of a, I don't know if triangular is the right word, but a branching pattern that looks like this. It's also equally valid to draw a branching pattern that looks like this. So instead of drawing these two coming to a point, we can draw sort of a bracket style. And this is saying that red foxes and swift foxes are closely related, and eventually they had a common ancestor that gave rise to man wolves and South American foxes. And then it also gives rise to this whole grouping over here. So both of these are equally valid ways to draw a cladogram. So when we're looking at cladograms, a lot of times you'll see traits that are sort of marked as little hash marks on the cladogram. And the hash marks are going to represent different traits that arose at different points in the cladogram or the evolutionary history. And so the way to read one of these hash marks is to say that, so let's look at this one first. So we're saying feathers evolved here. So we're saying that on this branch of the evolutionary tree, only the organisms that are downstream of this branch are going to have feathers, because that's the point at which in our evolutionary tree feathers evolved. And so this is a sort of isolated examples because feathers only are connected to one branch. But if you look at this one, so if fur evolved here, then the common ancestor to both chimps and mice had fur. And so both chimps and mice are going to also have fur because their common ancestor had already evolved fur because it came about here. We could go further back and say claws are going to evolve here. And so that means that every organism past this point, so lizards, pigeons, mice, and chimps, will have claws or nails. And that's because the common ancestor to all of those organisms, which is represented by this point where my laser pointer is circling right here, this common ancestor had claws because the claws evolved prior to that common ancestor existing. The word that we use for traits like this that organisms are going to share because their common ancestor possessed that trait is called a homology or a synapomorphy. They're synonyms. Homology is probably easier to say, or a homologous trait. So if you're thinking about two organisms and they share a trait because their common ancestor had that trait and passed it on to both of them, that's called a homologous trait. So you can see the same thing for, let's say, lungs down here. This common ancestor that exists at this node had lungs, and so salamanders, lizards, pigeons, mice, and chimps all have lungs because their common ancestor possessed it and passed it on to all of them. So that's one way that two organisms can share a trait because their common ancestor had that trait as well. However, you can imagine that there are some organisms out there that share traits, but it's not because they shared a common ancestor with that trait. One example is fins. So if you've ever looked at the way a lot of underwater organisms have fins, so fish have fins, but also a lot of, or not a lot of, you can think of like whales or dolphins or porpoises, those have fins as well. But they don't have a recent common ancestor with a fin. So they didn't inherit that fin from a common ancestor. And it's especially apparent if you look at the way the fins work in fish and underwater mammals. Underwater mammals move their fins almost like a horse would, up and down vertically, whereas fish move their fins from side to side. So these fins in fish and porpoises, let's say, they evolved separately, not from a common ancestor. And a lot of times this can happen if organisms are living in similar environments where similar traits would be helpful. Natural selection can select for the same trait in two separate branches of an evolutionary tree. So the word for this, we can't say it's homologous because they didn't get their fins from a common ancestor. Instead, we call it homoplasy. So homoplasy is when two organisms share a trait or two species share a trait, but it's not because they inherited it from a common ancestor. And like I said, this is usually caused by similar environmental pressures causing that trait to be helpful and selected for in two different branches of an evolutionary tree. And it's often, almost always, caused by what's called convergent evolution. And convergent evolution just refers to a process where evolution selects for the same trait in two different branches of a tree. So another example could be that you could think of like butterflies having wings and bats having wings. The common ancestor of butterflies and bats did not have wings, but both of them, through the process of natural selection, wings were helpful and it evolved separately in both of those organisms. So convergent evolution is when a single trait is selected for in multiple lines of an evolutionary tree. And the result of that is homoplasy. Okay, so we've got one last slide. Oh, here. This is the one that I want to skip through. So the last thing I want to go over is if this idea that we can have either homologous traits or traits can evolve separately in different branches, then how do we know which tree is more likely than another? We could either have one trait evolve once and then put everything that has a trait sort of after the evolution of that trait, or we could just make that trait evolve a bunch of times and put those organisms on separate branches, right? One sort of guiding principle when you're building a tree is the principle of parsimony. It's also called Occam's razor. And this is this idea that if you're all other things being equal, choose a simpler explanation. So particularly for tree building, if you have no other evidence to the contrary, it's better to have a trait only evolve once, because it's just more likely that a trait's going to evolve once and get passed on to a lot of different organisms than have a trait evolve a bunch of different times. So if you're sort of deciding between two hypotheses about where a trait could evolve, it's better to just have it evolve once and then be passed on to the sort of downstream species on that tree. So this principle of parsimony, or principle of Occam's razor, choose the simplest explanation that will fit the evidence. Okay, I might make another video to follow up on this with some misconceptions about evolutionary trees, but I'll cut this one short here since I just went over sort of the important bits that you'll need to know for now.